So this should be full screen for you.
Yes, it's working. Yes, we can see
Okay.
that. So let's move to this last talk, or this is morning session by Enrico Rinaldi, who's going to talk about machine learning for supersymmetric matrix models. So
yeah,
please.
Thank you very much for the opportunity to describe this work. I hope it's not too far from the topics of high energy physics touched upon in this workshop, but I actually think it would fit probably nicely with what was described in the morning today. So I will describe what are called matrix models. And so I would have to introduce them because they may be unfamiliar to some of you. Are you able to see my second slide? Is it working? Okay. Then I will describe some of the numerical techniques that people are using to solve these matrix models. And in particular, I will describe a quantum computing approach and a deep learning approach. The usual approach is to use a path integral Monte Carlo, which is the same technique used in lattice QCD, for example. And then I will conclude and describe some of the challenges for the future. Probably I won't have time to go through the details of the standard way of solving these theories, and I will focus mostly on the new development in quantum computing and deep learning. So what is the motivation to study these matrix models? And for me, at least, the motivation is coming from quantum gravity. I'm defining a theory for gravity that is compatible with quantum field theory. And for that, we actually look at some guidance from the holographic duality, which tells us that a quantum field theory actually is a gravitational theory, where this correspondence between quantum field theory and gravitational theory can be used both ways, both from one side, from the quantum field theory side, to understand something about gravity, but also from the other side, from gravity, to understand something about quantum field theory. And one nice feature of this is that this holographic duality could provide a fully non-perturbative definition to superstring and M theory. And this is, of course, through this duality, so through the quantum field theory side of the duality. And in practice, this duality is connecting a supersymmetric quantum field theory to a theory of gravity with some metric. And today I will focus on matrix models, where this supersymmetric quantum field theory is a 0 + 1 dimensional maximally supersymmetric gauge theory. And on the other side of the duality, we have basically a black hole in some string theory. But what I care about, what I want to do numerically and computationally, is to solve the quantum field theory side of this duality. And in the past, we actually were able to find this dictionary numerically and prove, in this case, the gauge gravity duality. But the theory that we are trying to solve on the quantum field theory side is rather different, at least from looking at the Lagrangian, from the quantum field theory and the standard model. But in reality, this is coming from a supersymmetric Yang-Mills theory with a UN gauge group in 9 + 1 dimension. If you dimensionally reduce the theory all the way to 0 spatial dimensions and just 1 time dimension. And what you see in this Lagrangian is the famous BFSS model, where the degrees of freedom now are SUN Hermitian scalars. So these are n by n matrices. That's why this is called matrix quantum mechanics. And we have these bosonic degrees of freedom describing in some pictorial way the coordinates of D0 branes and their coupling in the dual theory. And the relation between this model of matrices and the gravity theory is a conjecture, but by solving both sides of the duality, we can actually prove this conjecture. This is the final goal that we want to solve using quantum computing and machine learning methods. And but there are some challenges that we are facing right now, and this is the main reason why we are looking at these new computational technologies, because in the past, as I said before, we actually did numerical simulations to solve these theories using high-performance computing simulations, which are completely analogous to lattice QCD simulations. But those simulations are facing challenges when you have a sign problem in your theory, or when you actually care about the full wave function of the states of your theory, and not just static quantities that we can compute using Euclidean path integral methods. So these challenges are the main reason why we are now looking at quantum computers and deep learning as new directions, new computational directions for studying these models, and gain some insights into quantum gravity theories. For quantum computers, what we're trying to do right now is to represent the wave function of the system using qubits. And so using a quantum physical system that is in the hardware of quantum computers. And for deep learning, we're trying to represent this wave function again using neural networks or generative models in particular for the remainder of my talk. I've seen some talks in this conference related to quantum computers, so I think I will also talk briefly about that. But first of all, let me introduce the models, which are not the full final goal, the BFSS model, but they are some prototypical models which are smaller in size, so that we actually can get some benchmarks. I will start from a bosonic model and then describe the supersymmetric model. The bosonic model has this Hamiltonian on the left, and these are only bosonic degrees of freedom, and the physical states are invariant under SUN gauge symmetry. So we can write these SUN matrices, these Hermitian matrices, in the basis of the generators of the SUN group. So what you have to remember here is that we can have up to D matrices X, and for each matrix Xi, we are expanding it in the basis of alpha generators, which are n squared minus 1 for an SUN group. Yeah, let me know if there are questions. Also, maybe write in the chat or something. Okay. For the supersymmetric model, we have the same Hamiltonian that we have in the bosonic model, plus some terms that include fermions and interactions between bosons and fermions. And here again, the fermions are SUN matrices. And again, we expand them in the basis of the generators of the SUN group. So we have n squared minus 1 of them. The Hamiltonian is, you can quickly see that there is a free term if you want some sort of just uncoupled harmonic oscillators. And then there is an interaction term that couples different degrees of freedom of the theory with terms that are up to 4 matrices with a coupling strength given by G squared. So as you turn on this coupling G squared, you get stronger and stronger interactions between the degrees of freedom. On the supersymmetric model, we have the same Hamiltonian of the bosonic model plus fermion boson interactions and some constant terms. And this supersymmetric theory on this side actually has 0 energy in the ground state. So actually, this is a good property due to supersymmetry, in our case, because it will allow us to have a good benchmark. So we know the exact value of the energy, and we will try to reproduce it using our quantum computing and deep learning architectures. Okay, so what's the problem here? The problem is that for bosonic degrees of freedom, we have an infinite dimensional Hilbert space. So if we want to put this theory on a computer, we have to use some discretization. And let's look at one small system where we fix n to be 2. So we have an SU2 group, and we fix the number of matrices to be 2 again. This is a prototypical system that actually has all the properties that we care about for the theory. So that's where we start. And the indices here go from 1 to 2 for I and from 1 to 3 for alpha. So in total, we have 6 bosonic degrees of freedom. And we have this coupling constant G. And when G squared is equal to 0, of course, all these degrees of freedom are interchangeable. They're all uncoupled. So you can think of this as just 6 harmonic oscillators. But as you turn on the coupling, you start having interactions, some sort, between all these degrees of freedom. And if you start from the vacuum of the theory, where all these harmonic oscillators are in the ground state, when G squared is bigger than 0, you don't know what this ground state will be. So the goal is to find this ground state when the coupling constant is larger than 0. How do we do this on a computer? We start by truncating the Hilbert space. And for example, if we just focus on these 6 bosonic degrees of freedom, we could represent each of them in the local Fock basis, where each oscillator is can attain up to lambda different modes from the ground state, which is mode 0, all the way to the maximum excited state locally of lambda minus 1. And the total Hilbert space is the tensor product of these local Hilbert spaces. So we can have all possible states from a state where all the oscillators have no excitations, all the way to the largest excitation mode. And so with this, we have a finite Hilbert space that we can actually explore numerically. If this cutoff value lambda is small, we can actually write down the Hamiltonian in matrix form and do exact diagonalization to find the ground state wave function and its energy eigenstate. However, the challenge is that the physical results are only obtained when this cutoff value is sent to infinity. So this would be the challenge. We would have to do some sort of extrapolation and actually understand what is the truncation error that we are making when we put this theory on a finite Hilbert space. This wasn't done before, but it's actually rather trivial to do. We just start from small values of cutoff in this Fock basis and write down the Hamiltonian and then compute the lowest states from the ground state all the way to, I don't know, the few excited states using exact diagonalization. And then we study the convergence of observables to the limit of infinite cutoff. And we start from the energy, which is a very simple observable because we care about the ground state. So we want to know what's the energy of the ground state for this model. And in this plot here, we can see that for a coupling constant, small lambda equal to 0.2, where small lambda is just G squared times n, and n is equal to 2 in this case, we can see a convergence, very quick convergence to the ground state energy when the cutoff is just about 6 or 7. Then we can see how this actually depends on the coupling. So if we have a strongly coupled system, can we still see this convergence with lambda or not? What happens? And we just changed the coupling, and we see that we still have convergence, but the convergence is lower. And in fact, we can plot this in a log scale and see that the convergence to the correct answer is actually exponentially fast. The second thing to do is to check that the ground state is actually a gauge invariant state, because so far we have not imposed any constraint on the symmetries of this state. And what we do is study the expectation value of this operator G, which when acting on a gauge invariant state will just give 0. And again, we see that this expectation value of this operator on the ground state goes to 0 exponentially fast with the cutoff. So even though we are breaking gauge invariance by truncating the Hilbert space and writing our Hamiltonian in a truncated Hilbert space, we can still reach the correct gauge invariant ground state as we send lambda to infinity. And for all practical purposes, actually, even a finite value of lambda around 8 is enough to get the correct answer. And this is true for many different couplings, all the way to strong coupling. Okay, so this was a benchmark. This was done exactly, but clearly there's a limit with the number of degrees of freedom that you can actually put in your system and still be able to do exact diagonalization. So we turn our attention to variational methods, which would be more efficient and scale better with the number of degrees of freedom. And for the quantum computer technologies, we actually try using the variational quantum Eigensolver, which is a variational method based on parameterized quantum circuits. So the wave function is parameterized using an ansatz, which is implemented on a quantum circuit. Okay, so it will start from the ground state of the qubits, and then implement a series of gates that are parameterized, so the parameters can be adjusted. And then these parameters are adjusted following the minimization of a cost function, which in our case is the energy. So we want to minimize the energy or the expectation value of the Hamiltonian in this trial state psi, and make sure that adjusting the parameters takes us to a minimum of this cost function. But the optimization of the parameters can be done classically. So this is a so-called hybrid quantum classical algorithm. The bound that we get from this algorithm is an upper bound for the ground state energy. And the parameterized quantum circuit with the optimal parameters theta star is a representation in a variational sense for the wave function of the ground state. We start from, again, this small scale system, and we discretize truncate the Hilbert space up to a cutoff of 2. So in this case, we only have a ground state and the first excited state, which means we can put our 6 degrees of freedom, each one on a single qubit, because a qubit is a 2-state system. Then we can choose a variational ansatz, which is this parameterized quantum circuit. And here we have many different choices. We just went with one so-called hardware efficient choice, which is implemented in most of the software frameworks that you can access for quantum devices these days. And this quantum circuit has parameters which enter the rotation gates Ry. So there would be, in this case, 12 parameters for 6 qubits when the circuit has a depth of 1, but you can implement more blocks of this variational form and increase the depth of the circuit, and therefore increase the number of parameters. And one can run this circuit starting from many different initial values of the parameters. Then we have to actually simulate this quantum circuit or evaluate it on a quantum hardware. We don't actually use any quantum hardware. We just choose a quantum simulator for our first benchmark, which is exact and doesn't have any noise associated with the actual implementation of these gate operations on actual devices. And then we choose different classical optimizers to minimize the cost function and find the optimal parameters. And we do this just to get a sense of how well this VQE method can find the ground state for our system. And this is an example, again, on 6 qubits. The exact energy that we have from the exact diagonalization method is 3.148. 0, and by running this variational quantum eigensolver, we can actually get very close to that energy, as you can see from the results in the table, and also from the plot of the VQE energy as a function of the iteration of the classical optimizers. And some optimizers are faster than others in getting to the ground state, and this depends on the number of parameters also. And when we increase the cutoff from 2 to 4, we basically assign more qubits to each degree of freedom, and we go from 6 to 12 qubits. And again, we can see good agreement between the energy that we get from VQE and the exact energy that we have seen before for this cutoff from exact diagonalization. This is these are results at small coupling, where the wave function is easier and closer to the harmonic oscillator problem. But when we increase the coupling, we have a more complicated wave function to describe. And these parameterized quantum circuits are actually getting worse with the strength of the coupling. So we see that the difference between the exact energy and the VQE energy grows with the coupling constant. So this is by using the same exact variational circuit for all the different couplings. But what we did was also to test how far do we need to go in terms of number of parameters and depth of the circuits before we can actually get close to the real answer. And we see that, for example, in the case of the supersymmetric model, where we also have fermions, we need to increase the depth of our parameterized circuits quite significantly before we actually get close to the exact answer. So this is one of the findings of our paper, which is the type of wave function, trial wave function that you use is very important. And people already know this for other systems where exact symmetries of the system have been already implemented in the circuits to help finding the correct wave function. Here, we didn't actually implement any symmetry at all. We just choose a very generic ansatz and tested how well it would perform. So there is a lot of work to do from here in order to make these methods useful for our purposes. But let me move now to the deep learning example, where the wave function is now represented by a neural network. So this is, again, a variational method. So the ingredients are the same as in the variational quantum eigensolvers. So we start by choosing a trial wave function, which is some neural network architecture that takes a configuration of our degrees of freedom and returns the wave function or amplitude psi. Then we compute the energy using Monte Carlo sampling by sampling from the Born distribution given by the wave function. And we optimize the parameters in the wave function ansatz by following for example, gradient descent, or using some other learning algorithms that are common in machine learning. For the wave function, we choose to use autoregressive flows as powerful generative models, and they have already been described today. But for the type of objects that we care about, I'm just going to give a short recap. We basically take the wave function as the product of an amplitude and a phase. The phase can be any fully connected neural network that depends on the configuration of the degrees of freedom x. And the amplitude is going to be a probability distribution, or the square root of this probability distribution, in such a way that the modulus square of psi x is given by this p of theta, so that we have a normalized distribution. Then we can choose for this p of theta a autoregressive structure and also a flow structure, where we start from a simple distribution for the latent variables, and by using bijective transformations with easily invertible and easily computed Jacobians, we can get some complicated probability distribution for our data or variables x. Here we don't have data for training. What we're doing is we want to do the sampling from this guy. And we choose to describe this probability distribution for each entry in our vector of x, which describes our degrees of freedom, in an autoregressive fashion. And the parameters for the distribution depend on a structure given by fully connected neural networks. So in this case, we are not discretizing the degrees of freedom. So we're not putting this into a discrete Hilbert space. We actually have continuous variables for our degrees of freedom x. So here we are not introducing a truncation of the Hilbert space lambda. This is one of the advantages of this machine learning approach. And we actually have direct sampling from the wave function by using this type of generative models. So these are two of the advantages of the deep learning approach that we take when we compare it to the quantum computing approach. The results are actually very similar to the quantum computing case, but now without any need for truncation. So we don't have any truncation error. We can actually explore the entire range of continuous values for the degrees of freedom. And even at large couplings, we can get very close to the correct answer. And we also see that the property of gauge singlet is maintained by the structure of the neural network. So G square, again, is the operator that should go to 0 if the state is gauge invariant. And here we see that it's very close to 0 with the numerical precision. And we tested several properties of this neural network architecture by increasing the number of hidden units in our hidden layer, and by testing it for various coupling constants from 0.2 to 2, so spanning an order of magnitude. We see that for the bosonic case with no fermions, we actually get results that are within the stochastic sampling error, are compatible with the exact diagonalization. Okay, for the supersymmetric case, we did the same, and here the result for the Hamiltonian should be 0, and we start to see for the choice of neural network that we have some deviations from the exact value, even within the error bars, when the coupling constant becomes large. And so this is due to the presence of fermions, which make the wave function more complicated. So in this case, if we want to go to larger coupling constants, we would have to change the architecture and make it more expressible by either adding more layers or choosing different representations, more efficient representations for our fermionic degrees of freedom. Let me get close to my conclusion, because I think it's lunchtime over there. We compared different methods to compute the ground state energy of matrix models for bosonic only models and for supersymmetric models with different gauge groups. For computational reasons, we can only do exact diagonalization when the gauge group is SU2, because for SU3, we would have too many degrees of freedom that we can actually not fit these Hamiltonians, even in their sparse representation on a computer, even for a small cutoff. But for SU3, instead, we can use the machine learning method because there is no, because the scaling with the resources is pretty good. We just use these neural networks and sample from a high-dimensional distribution. And we can always use path interval methods in all cases. And we can compare, for the case of SU3, what we get from the deep learning method and from the Monte Carlo sampling method on a Euclidean lattice. And we actually see that we have a very good agreement. And the error bars that we get from the machine learning method are actually smaller than for the Monte Carlo method. And the machine learning method is a lot faster to train in this variational modality than doing all the path integral Monte Carlo simulations. So let me conclude. What I wanted to show today was that quantum simulations and deep learning methods can actually be used to gain some insight into quantum gravity problems, mainly by following this holographic duality road. And we tested these hybrid quantum classical algorithms, namely the variational quantum Eigensolver, to show that we can compute the ground state energy for small size matrix models. And just by using what's available right now in the open source community, we could only get to small size systems, but this is just the first step towards larger systems. And for that, we would have to develop new simulation methods and new theoretical methods. For the deep learning method, I've shown that fast sampling from generative models is actually very efficient to get the ground state of these matrix models. So this road can actually already be taken to go towards the final goal, which is the BFSS model, which is larger n, so large matrices, and many more of them, all the way to 9 bosonic matrices. So we actually have a roadmap, both on the quantum side and the deep learning side, which includes finding better representation of these degrees of freedom on quantum on qubits or qudits or multimode or other type of hardware that's available right now, but also to improve the variational ansatz in both the quantum and the machine learning case, and to study the role of symmetries in the training of these methods. And one thing that I think is very important, and I really thank the organizers for giving me this opportunity, is to actually engage with different research communities to see what they're doing when they apply these methods to different fields of science, from quantum chemistry all the way to astrophysics. Thank you very much. And let me also thank my collaborators.
So thank you for the talk. Are there questions for Enrico?
Yeah, hi. Thank you for a nice talk. I guess I have several questions because I'm probably confused. First of all, I'm used to think of the sign problem as a problem of integrating a highly oscillatory function that goes, positive, negative.
Yeah.
And I don't. Is there a connection of that to this variational quantum ground state?
So the connection is this problem exists if you try to do Euclidean path integral Monte Carlo for problems that have, for example, chemical potential, or if you try to compute real-time dynamics. And in that case, yeah, you have this imaginary action. You have an e to the is instead of e to the minus is in the integral. So you can actually not sample from a probability distribution. So your Monte Carlo doesn't work. This is the same sign problem that you are referring to.
Yeah,
but
I guess. All right. So maybe I'm confused. What is the connection of doing the integral to doing the ground state? Because I thought you were doing the ground state in these variational calculations.
Yeah. So here, in this case, we are computing the energy of the ground state, and that can be done. There is no sign problem here, and that can be done in path integral Monte Carlo. And this is just the first step to test the methods, just to have a benchmark on both sides. But if these methods are efficient already to and can be used already to compute just the energy, then we can start moving forward and compute other things that are not that we cannot compute in the Euclidean path integral way because of the sign problem. So if we want to do scattering or real-time dynamics, thermalization, those dynamical properties cannot be addressed using path integral Monte Carlo methods.
I see. So basically, you're not doing any integration at all. That's your proposed solution. And
Right.
Can I ask another question? I mean, at some point, you're modeling this. I mean, a few slides back, you have this wave function model, and you're plotting a flow. You're plotting a normalizing flow, or something. Yeah, maybe this one. Yeah.
Yeah. This is
no.
Just
no. Yeah. Okay. This. Yes. What is this flow for which quantity now? Is this for psi absolute value or for phi? Sorry, theta. Or...
So here we are representing the distribution of x. So x is our capital X is our configuration, which is just a vector, which is the value of the bosonic matrix xi alpha.
Yeah, but you're showing a plot which is for normalizing flow, right? Which models the probability distribution.
Yeah.
But up there you have a wave function, and you're trying to decompose the wave function into the absolute value and the phase.
Right. So this P, probability distribution P, is the object that we use.
Okay. Right.
To represent the wave function.
Right. And okay, so this goes back to my question. Like, you're assuming P of theta is positive, right?
Yeah.
Which is not the case for fermionic things with blah, blah, blah.
Right. That's why we don't use. This is not used for fermions, right? This is used for bosons X. Yeah. So just, for your comment, it's not written here, but for fermions, we add a extra neural network that depends on fermionic degrees of freedom, and that is just a fully connected neural network. And that's why when we have fermions, we have a better than optimal agreement with the exact results, because we don't have enough parameters there or enough structure to do a good job to represent a wave function that includes fermions. But people are working on fermions right now in the quantum many-body community, so we are actually planning to look into those techniques. So our normalizing flow is just for bosons, for these continuous variables.
Okay, thanks.
Okay, I don't see additional questions, so let's thank Enrico again.
Thank you.